And we're good to go. Okay, so much like this isn't any different than you guys calculating like displacement, really, right? It's just we're in a different context now, right? So what we've got here is we've got a whole bunch of what we call forces. So like friction and an applied force. So you're pushing on a box would be like an applied force. And then we've got the force of gravity and a normal force. Okay. What a normal force is, anytime, like if this is a box sitting on a counter, right? Okay, the reason why the box doesn't just go crashing through the counter or table is because there's a weight, right? The box is weighed down, but the table that it's sitting on pushes back with an exact opposite force. That's how it doesn't crash through, right? There might be a point in time where this box has such a weight that it's such greater than what the table's actually able to push back with, and then it crashes through the table, if that ever existed, right? The legs would probably collapse, something would happen, right? The normal force that the table would be able to apply back on the box wouldn't be able to equal the weight of the box, and that's why it crashes, right? It goes right through. Is that okay? So that's one of Newton's laws, which we'll learn later, right? And you guys probably have a little bit of familiarity with Newton's laws. You probably heard them, like an object at rest stays at rest, things like that, right? But for today, just this morning's lesson, like we just want to kind of get a familiarity with what free body diagrams are, right? And calculating net forces, right? So with this is what we call a free body diagram, all of this, right? An FBD. And free body diagrams don't go away. It doesn't matter what level of physics you get to, right? We always draw the scenario. It doesn't need to be like a fancy book or anything like that, right? But we can draw a square and draw the forces that are acting on that square, right? Or box, whatever it is. Okay? And so to find the net force, we've got two things going on here, right? I have forces, and you guys, this is why I'm happy about the order in which we've done things, because we've already kind of talked about, we have forces acting in the y direction, and we have forces acting in the x direction. They're both separate, right? And you treat them separately, because if they're acting in different directions, then they're going to affect the box differently. If we're trying to predict the motion of this box, ultimately, right, then x and y have to be treated separately. Okay, that's how we're going to be able to answer these questions. Now, you can imagine these questions are kind of nice because the forces are acting directly in the xy plane, right? But there's not saying, and this is what tomorrow is, that we don't have a force applied here at an angle, which you guys now know how to deal with, and we're going to look at that tomorrow. Okay, but we're just going to cover some basics here this morning and today. Okay. Anybody have any questions? That's where we're at. Okay. So if we want to figure out what's happening to this box, well, or any box, like that's what the free body diagrams do. We're going to look at the forces acting in the x direction, and we're going to look at the forces acting in the y direction. All right? And you're always still going to apply some form of grid system, right? Where we say up is positive, right is positive, negative, negative, okay? And so what do we see? Well, in the x direction, it looks like we have a frictional force and we have an applied force, right? So I'm pushing on a box and friction is acting in the exact opposite direction, right? So we see, okay, what are the forces acting? Well, I have negative, the force of friction, right? Because it's acting in the negative direction. And I have a positive, because it's acting in the positive direction, positive, we'll call it FA, applied force. Okay? And then in the y direction, we have the positive normal force, Fn, and we have a negative force of gravity, right? Because it's acting in the downward direction. Now what you guys can do is say, okay, great, I know what the forces are, I've separated them, right? You guys have separated them into X and Y. Let's figure out what's going on, right? This is almost like breaking things into components, right? You had the two separate sides of the table, right? And we're going to say, okay, let's fill in the numbers because I'm given the numbers. All right, well, I'm going to have negative 5 newtons. We'll discuss what a newton is later this afternoon, right? Plus 5 newtons. Right, so you say, okay, well, negative 5 plus 5, oh, that's 0 newtons. So the net force, we could say F net in the x direction is 0 newtons. So let me ask you a question. If there's no forces acting on a box, is the box moving? No, right? So if you're not applying a force, right? If you're not pushing on anything or creating an imbalance in the net force, then the object's not going to move, right? And so what you're going to see here is like a box sitting on the table just doesn't spontaneously decide to jump up, right? So you're going to see that here as well, right? So we have a positive, we have 3 newtons for the normal force, and then we have a minus 3 newtons for the gravitational force, right? The force of gravity. And that's also 0 newtons. And so F net Y is equal to 0 newtons as well. And so we can conclude by looking at both of these answers. It's key to look at both, right? When I look at both of these, they're both 0, right? And so the box isn't moving. Is everybody okay? That's conceptually not too bad, I don't think. I'm going to shrink that down because I need some more space. I love the iPad for that. That's wonderful. Okay. Let's look at the second free body diagram. It's just a box, right? Looks like the box is maybe falling in air, right? And what do we got? Well, we don't have, like, there's nothing forcing the box in the left or right direction, right? Or in the positive X, negative Y. So I don't have any forces in the X direction. With no forces, right? But in the Y direction, you're going to have, okay, well, let's look at the forces. We have positive force air and minus the force of force of gravity. I should probably draw. Forces all have vectors. They're all vectors, eh? That's a little bit formal, but they're vectors. Important to specify that they're vectors. Okay, and then we just plug in the numbers. We're like, okay, well, what's happened? Well, we plug in the fact that the force of air is 40 newtons, right? So positive 40 newtons, and we're going to minus 25 newtons. And that difference is 15 newtons. Okay? Anybody have any questions? If the force is being applied in the what looks to be the net force, right? So F net appears to be on a positive 15 newtons, right? So what direction would we expect this to be moving if it's in the positive direction? Up. That's what I would expect, right? In context, I don't exactly know in context what that would actually look like. But in the math sense, we expect this thing to be moving in the upward direction because our answer came out to be positive, right? So it should be moving up. Okay? So Well, this one. Well, this one looks like, well, I don't have any y this time, right? We only have x's. Well, it looks like, remember, you're always going to have a coordinate system. Positive this direction, positive, negative, negative, right? If that means north, east, southwest, I'm okay with that as well, right? We're going to say, okay, well, we've got x's, right? And we're going to say, okay, let's calculate. Like, we got to find out what's going on. And sometimes it's easy for these questions. There's a reason why we're starting with this question, because it's a little bit easier, right? When we get to tomorrow, there's nothing different in the principle. The only thing that changes is the forces that are acting on the box, right? That's the only thing that changes in principle, right? It's just the math gets a little tougher, right? Because now we have forces acting at an angle. But the principle or the idea concept is the exact same, right? You gotta figure out what's acting in the x and what's acting in the y, and figure out what the motion looks like, right? That's it. So we're gonna say, okay, well, I've got positive F2, little arrow, and negative F1. All right, you say, okay, well, let's fill in the numbers. So I get positive 18 newtons minus 20 newtons. So it looks like I'm going to get negative 2 newtons as my force here, right? I suppose as you guys are going here, and like I'm kind of not doing this on the fly, but kind of catching things that I think maybe is worth noting. F net x would be equal to this. And I suppose as I write that down, I'm prompted to say, okay, what are you guys doing here? It doesn't matter how many forces are here, right? If I put another one on here and another one here and whatever, as long as they're acting in the x direction. What you guys are doing on the right-hand side here, right? And we're going to see this a little bit more like formally later. But what are we doing? We're adding up all the forces that are in that direction. What's that? Does anybody know what another word for adding up is? Like like turn your physics brain off and just think about math for a second. What's another word for add, or some synonyms for add? You guys know? Sum. Good, Jagger. Plus, yeah, the one I'm looking for is sum. Okay. Does anybody know, just out of curiosity, what Greek letter we would use? And I don't even actually know. Do I know them? Oh, I do know. What Greek letter would we use to represent sum? Do you guys know this? This is a little bit more advanced. I'll be impressed if you guys get this one. Okay, so I'm looking for the Greek letter that represents sum. Sigma. Yeah, it's like a capital E, Jagger. So for those of you that don't know what sigma looks like this. You guys have seen this before. Okay, this means sum. I'm gonna move this up here one sec. Okay, so this. What are we doing? We're summing all of the forces that are acting in the x direction, right? So what we might say here is, oh, I'm running out of room. I have so many good things to say and I'm running out of room. Okay, what we might say formally is the sum, oh boy, you guys will learn to write this thing out. Sum of the forces in the x would be equal to positive F2 minus F1. This is maybe where we're going to head, okay, this afternoon. We're just adding up the forces that are acting in the x direction, and subsequently you could get the sum of the forces in the y, right? Whatever they are. Is everybody okay? So we know, based on our answer here, we know that this thing's moving f net x. Or the sum of the forces in the x direction for this question is negative 2 newtons. And so we know if the net force is acting in the negative direction, then the object should be moving in that direction. Is everybody okay? So we're using free body diagrams to examine what could possibly be happening to an object, okay? And looking at the forces acting on that object and figuring out what's going to happen to it. Doesn't matter how complicated or how many of the forces that are there. You're going to break them down into x and y, just like components and vectors, because that's all these things are, is vectors, right? And you're going to figure out, you're going to get a net vector at the very end, a resultant vector, and it's going to tell you what direction the thing's moving and how much force. And eventually we'll be able to figure out how fast it's moving. That'll be this afternoon. Or what rate it's changing its velocity, okay? Is everybody okay? So one of the other things that we can do is, if I tell you what F net is actually equal to, you guys can find the value of other forces. And that's what these 4 pictures down here are doing for you, right? So for picture 1, it's telling you that F net, so this box isn't moving. This is like this scenario, right? So you guys know, okay, well, if this box isn't moving, what color do I want to do? If this box isn't moving, then I must know that vector A, because it's acting in the x direction, if it's not moving, vector A has to have a value of 50 newtons in the negative direction, right? Which you could stipulate as being negative, or you could say 50 newtons east. Sorry, not east, west. Right? So you know vector A is this. And then also, if you know that the net force is 0, then you also know B should be positive 200 newtons. Okay, and when you guys draw arrows on, like for the purposes of free body diagrams, if you guys are very specific and clean with your free body diagrams and you just label this thing, right? If you have a clear Cartesian grid and you're saying that for every question that you guys do, if you say that there is a clear positive, positive, negative, negative, and you have a box or a free body diagram, right? I'm okay if you guys just say, okay, well, my free body diagram is this. I have a force of 50 newtons in this direction. If it's acting, if you guys draw the arrows on here, this is what's nice about free body diagrams. I know it's negative because you told me it was negative with your coordinate system, right? And if I have 50 newtons in this direction, I know it's positive because the vector is telling me it's positive, right? So we okay? It's the importance of, and that kind of gets to my, I maybe didn't emphasize that enough when we started this with the display, like the vectors and the displacement and the velocity and things like that. And that's what was missing off of your formatives. If you're asked for some form of vector, you have to include the direction somehow, right? If it's up, positive, negative, north, east, south, west, like tell me the direction if you're asked for a vector, okay? Displacement, velocity, whatever, doesn't matter. You now know what vectors are. Make sure you're including the direction. You can see here, they've included a direction here, 50 newtons up. Right? And so what are we going to get here? Well, I'm going to get you guys in the habit of writing things in a formal way, right? So this here, I only have forces acting in the y direction for this question, right? Up and down. Right? And so if I know that there's only y forces acting, well, then I can write the sum of the forces in the y direction. Oops, I need the F. In the y direction. We know the net force, that's equal to 900 newtons, right? Well, I'm going to sum the forces, this is what this is telling me, in words. Sum the forces in y, right? That's what this is saying. It's just a fast way to say it, right? That's why we introduce fancy symbols and letters and things, right? So we don't have to write this out all the time. That's all that is. That's why I think people get scared by looking at physics or math sometimes, right? Because they see all these fancy variables. They don't mean it. They're just something to solve for, or like you string a couple of them together. You guys would have seen like XER, things like this, right? This scares people sometimes. Oh, it is. It's just it's a catchphrase that's just put into some letters, right? That's all it is. So when you see this, it's just a formality. It's the sum of the forces acting in the y direction. Well, what do you have then? You know this has to equal 900 newtons. Okay, well, what are the forces acting in the y? Well, we have negative 200 newtons plus c. Solve for c. How do I do that? Well, create a zero pair. Right? What you do to one side, you got to do to the other. And you can find the value if I tell you what the net force is. Right? So you say, okay, well, c is equal to 900 newtons minus 200 newtons, plus 200 newtons, sorry. Right? So c equals 1100 newtons. Okay? Are you okay? So these last two, they aren't telling you anything like, it's telling you F net is acting in the left direction, right? It did not give you, so an example of a force that is acting in, you guys know what this looks like, maybe just, I have to spout out for you once, right? If F net said something like, I don't know, 600 newtons east, 50 degrees north. This is a bit of a harder problem. We're going to see this later, right? This implies that the box is going to go like this. Like that's the net force acting. It's not pure X. It's not pure Y. It's somewhere in the middle, right? That's not what this question's saying. Okay? This question's saying that the net force is acting in the X direction, right? Left. Which tells you that in the Y direction it's not moving. Right? So that must mean right off the top, if it's not moving in the Y direction, then E must be 300 newtons. Negative 300 newtons, sorry. Oh, this is a new one. There we go. Okay. And so then you just do the same calculation, right? Except this time we're dealing in X, and I'll continue trying to use like red and blue because I think it's effective. Okay. So you say, okay, well the sum of the forces in the X direction is equal to negative 60, sorry. Why is it negative? Because it's left. And we're saying positive, positive, negative, negative. You guys have been doing that for years and years and years, so keep with it. Right? It's effective. You don't mess that up. Say it's acting to the left. All right, well, let's add the forces together on the X side then, right? What forces do we have? We have negative 80 newtons plus D has to equal negative 60 newtons. All right, solve for D. Well, D has to equal negative 60 newtons plus 80 newtons. To the right, I'll add that. Okay, if you guys can do this, there's a good starting point, right? You kind of start at a basic level, and then from that point, we just take the knowledge that we've built over the last 3 or 4 days on vectors and breaking things into components, and that's as hard as the questions get. Where it's just this with components, right? And then the only other layer with this is like, okay, well, what's the acceleration of the box, or how fast is it moving, things like that. You can use Newton's laws, and that's what we're going to learn this afternoon, to answer questions like that. If I push on a box, what's its acceleration? That's what we're going to learn. Okay? Anybody have any questions with that so far? So that's an introduction to free body diagrams and forces in general. And we can have all sorts of forces, right? We can have things like, if you have a rope attached to a box, that's tension. Tension is a force. We have friction. We have gravity. We have normal forces. We have applied forces, whatever those look like. Okay, the list goes on and on and on. Okay. I suppose the only trick is like correctly identifying the direction in which those forces get applied to the object. That's the only trick with these questions. And it really comes down to free body diagrams. If you draw one of these things every time, it adds an extra layer of understanding and clarity for what you're trying to do in solving. Okay, so what I'm going to do is jump down here. We're going to see these pretty relentlessly, and they don't go away. If I pulled out my first year physics notes, they're there again. Okay, we have to know how to label diagrams like this. Okay. Okay, so let's, for one moment here, this throws a wrench in things, a question like this. Okay, and the nice thing is, when I'm given a question like this, you guys have some flexibility in what you're allowed to do in terms of a coordinate system. Okay, so to make questions like this easier, right? Well, you'll notice, maybe I'll start with one thing in particular, right? This box is sitting on this ramp, right? And so from up above, we learned that if something's sitting on, like even this question here, we learned that there's a normal force. And does anybody have the fancy math term for something that looks like this, that meets at a 90 degree? Does anybody have the math term for that? Things that meet at a 90 degree angle. Starts with a P. Perpendicular. Okay, good. So the normal force is always perpendicular to the surface in which it makes contact with. Okay, and that's what throws a wrench in these kinds of questions, right? Is we have this normal force acting perpendicular to the surface in which it's touching. Okay, so this is Fn. Okay, so always perpendicular to the surface it's in contact with. Okay, now let me ask you guys another question, because this is where questions like this are a little bit tricky. How does gravity affect us? Do you guys know? In terms of in the direction that it acts in. Always down, directly down. So something like this, Jagger's saying, right? We agree, and that, again, you're seeing some benefits of the iPad here, because I'm going to do something in a sec. I think everybody would agree with the fact that the force of gravity would look like this. That's not a it's not that it's a no-brainer, but I think everybody agrees with it, right? So what does that look like in reference to our picture? Well, if I take this vector that we all 100% agree on, and I move it over here, this is where the problem kind of starts to arise, right? Because we get these funny angles and things going on now, right? And it brings in the need for components. I'm going to move this to the outside. Okay, so this, on an incline, this is what the force of gravity looks like. Okay? Because the force of gravity is always acting straight down. So which means this is now, relative to this Fn, this is acting at an angle. Or you could think of the Fn acting at an angle, right? And so what are you going to get? Well, if as soon as I mention the word angle, you guys got to be thinking about components, right? If you see an angle, theta, whatever it is, you got to be thinking components. And taking things and breaking them into their pieces. As soon as you see an angle, right? Well, what's that mean? Well, it means I have a y piece that is opposite of Fn, right? It'll be well, it's opposite in the direction. It can't be opposite in magnitude, though. Okay? And I also have an x piece. Now, what you'll notice is the x piece, and this is something I always kind of struggled with too, learning this for the first time. The x piece, when you guys draw these, should be parallel to the incline. Okay? This is a special piece here, right? This is FGX, right? And the blue is going to be FGY. Okay? Actually, these have to be. Let me correct a previous statement. Now that I'm thinking, because I wasn't thinking. These two things, we just talked about this. Fn and FGY have to be equal to each other. Why must they be equal to each other? Because if they weren't, this thing would go crashing through the incline or flying up off the incline. That doesn't happen, right? So it's conceptually makes sense that those two things have to be equal. Okay, and we can use that to our advantage as we start solving problems, right? So there's one other little catch here. So you're asking yourselves, well, how do I find the values of these things, right? Well, most of the time, if I don't ask you specifically for what this angle is, it's going to tell you it's like, let's say 30 degrees or something, right? You guys know through geometry that this is 30 degrees as well. That's just a given. Okay, you don't have to understand why. It just is what it is. Okay, these two angles match. Okay, so what does that mean for this question? Well, it means if I were to find this, then FGY would be equal to what it, oh, we haven't discussed this yet. Do we know what FG is, the force of gravity? We're going to do that next. We're going to do it next, like in the next page. So I'm just going to show it to you now anyway. The force of gravity, you guys can always calculate what the force of gravity actually is. It's something's mass, right? Multiplied against the gravitational field that it's in, right? On Earth, right? So on Earth, right, we're going to say, okay, well, the force of gravity that we experience on Earth is something's mass times negative 9.8. This is why this is a special number, right? And so the force of gravity that you feel would be whatever you weigh, or not what you weigh, what your mass is, times negative 9.8. And that's the force acting down. That's what the negative does for you. Okay? So in the instance, you guys now know that Fg equals mg, right? So you know, how do I calculate Fy? Fy you can calculate as, well, it's the force of gravity sine, oh, sorry, careful, cosine theta. Now, let me do the other one, and then we'll discuss, because I'm sure some of you are freaking out. How can the vertical thing be cosine? This is the instance. So for kinematics, to break things into its components for kinematics, things were a little bit easier. Okay, for these kind of force questions on an incline, you guys got to pay attention to, if I were to draw this triangle here, what side, if I draw the angle there, what side length is this relative to the angle? This side length is adjacent. and this side length is opposite and hypotenuse. Which means for this side length, or the y component, I'm going to need cosine because it's adjacent over hypotenuse. And for this side length, we're going to need sine because it's opposite over hypotenuse. That's where these two things, that's why they look flipped here, because the triangle is kind of flipped. But the angle that you're interested in has changed. Okay, this is a lot right now. We're just going to keep hammering away with questions like this. So you're going to see this over and over and over again, okay? This isn't going to go away, okay? So we're going to see, you're going to get some experience to actually work with this stuff. Now, what is the controlling factor as to whether or not this thing moves down the incline? Do you guys know? I just said that Fn and Fgy are equal, right? So it's not going to fly off, right? So that the thing, obviously, like if this is going to want to slide down the incline, right? Under one condition, and we're going to learn about this condition later. I'm not too worried about it, but you can have the force of friction, right? And then so this little force vector here, this one, is the other force here. This would be mg cos theta. Are we okay? That's a lot. Okay, and we're going to, yeah, friction, Jagger. Okay, so as long, if you guys are asking yourselves the question, how do I know if this thing's going to slide down the incline? Well, let me pose that question. Down the incline? Well, in order for that to happen, mg cos theta, mg sine theta, has to be greater than, not equal, force of friction. I'll make that capital F. Okay, if this thing here, what's that saying? This is saying this force right here, if this one is bigger than this one, then it's the motion is going to be in this direction. Okay? If the force of friction is bigger, then it's not going to move. It's going to sit there on the incline. We're going to talk about friction. Don't stress this. I'm just introducing things today. Okay? Trying to introduce some components and free body diagrams is the point of this lesson. When you guys go to look at the homework for this lesson today, be like, oh, it'd be like a sigh of relief. It'd all be stuff like this. Okay? Calculate the net force. And when we come back this afternoon, I'll step you guys through questions. I just want to introduce you to another style of free body diagram here. That's the point. Okay? We're going to continue to work with this page, these kinds of questions later. Okay, so it's okay if this seems overwhelming right now. We're going to keep hitting it. Okay. So last thing we want to hit before you guys go. Okay, so I just want to make a clear distinction between mass and weight. You saw as I was running through this question here, I caught myself once. Okay, there's a distinction between mass and weight. Okay, mass is the quantity of matter in an object. Okay, why is the opposite of friction mg cos opposite of friction? Max, you want to elaborate on that. Opposite of friction mg cos. I wrote it down wrong. Thanks, Max. Sorry, I wrote it down wrong. That's because all kinematics is still in my head. It's mg sine. Okay, it's mg sine. In case you guys are freaking out, it's mg sine because of this. Okay, I just wrote it down wrong. Okay, so we can't change the mass of an object. Okay, it just is what it is. Okay, and it's based on the amount of matter that's in the object, right? And what if so I think a clear distinction to be made would be like if I took 100 if I took the mass of an object, right, this M, it would have a different weight on Earth versus Mars or something, right? The mass is the mass. Weight is what's measured under a particular gravitational field, right? So weight is the force of gravity on an object, okay? And that's when you stand on a scale, you're measuring your weight, right? In order to figure out what your mass is, this is a clear distinction, right? So when you stand on a scale, the scale is pushing back on you with the same amount of force. You're measuring a force. What kind of force? The gravitational force. We just learned that the gravitational force is mg. So what are you measuring when you stand on a scale? Your weight, not your mass, right? Okay. If you wanted to find your mass, then you could take the number that you're reading. It's kind of, because it's like, let's say 150 pounds. That's a weight. It's not your mass. That's what you measure when you stand on the scale. If you wanted your mass, you'd have to take that and divide it by 9.8. Okay, so this page just makes the distinction for you, okay? As you can see here, to calculate the force of gravity, we use this formula. This is what I showed you on the last page, kind of just in context relative to the question we were working on. We always measure forces in newtons, and forces are vectors, right? Mass in kilograms, and gravitational field strength, okay? It's interesting because we always say, oh, when I stand on a scale, I weigh 150 pounds or kilograms or something, right? But it's actually measuring newtons. It's a force, okay? And we'll deal with a little bit more with this later. This comes out of some dimensional analysis, right? We can see, and we can see it more with Newton's laws as to where this came from. Okay, and we're going to see that this afternoon. Okay, so on Earth, the gravitational field, there you go, 9.8. That's where that number comes from. And then some dimensional analysis is just telling you what 1 Newton is actually equal to in kilograms meter per second squared. And we're going to see where that actually arrived from this afternoon. If an object is in free fall on Earth and the only force acting on it is the force of gravity, it will accelerate at 9.8 meters per second down. And here's a little spoiler alert for this afternoon, which you probably have all seen before. F equals ma. That's what we're going to look at this afternoon. Okay? So on